Our next lesson will be on equilibrium 3, which deals with equilibrium shifts. And in this lesson, we're going to look at two things. We're going to look at moving to equilibrium, that is looking at how to find equilibria constants or find information about concentrations from equilibria constants whenever you only know the initial amount of something, and then moving to equilibrium constants with unknowns whenever basically you have to do something, you have to basically find a concentration and you don't really have enough information to solve it using a standard method. We'll look at some tricks to solving equilibrium equations that way, equilibrium calculations that way. So here's what we know is that based on what we talked about last time, to find the equilibrium constant, we need to know the equilibrium concentrations of all the substances involved in the reaction. Because, we had to know those concentrations, and we had each of the concentrations, the ones on the right side on top, the ones on the left side on the bottom, each of their concentrations raised to their coefficient power. But if we didn't know one of those equilibrium concentrations, then we really wouldn't be able to find the equilibrium constant. But oftentimes, if you're doing a reaction, is that you generally know how much of each thing you put into the reaction, but don't often know how much you end up with. You need some way of, you've got all these things mixed up in your reaction vessel. So you put them on to start with, they all react, they reach equilibrium because you have a reversible reaction, but it's sometimes very difficult to measure each one of them, what their concentrations are at the very end. And so we do have a method, though, we're going to talk about here, that if you know just one of the final concentrations, that tells you what the change in concentrations of one of your reactants, one of your substances that you're involved in this reaction here, then you can use that to find the others. And the reason why is if you know one of their changes, you know that in any reaction, the change of one is in mole ratio to the changes of all the others. Remember all those coefficients out there? Those coefficients basically tell you what the mole ratio is. If you have a 2A plus B yields 3C, then you know that since it's 2A plus B, that you need twice as much for A than you do for B, and you need 3 times as much for C than you do for B because it was 2A plus B yields 3C. This mole ratio is going to let us figure out what the final amounts are if we know all the initial amounts of what we start with here. So, an example here. So, if the reaction that we have down at the bottom of 2NH3, reversible reaction to N2 plus 3H2, if we know that the concentration of N2 of nitrogen increased by 1.5 molar, then we can find the concentration of the other two, because if we know that this N2 right here increases by 1.5 molar, let's take a look at the NH3. Well, what's the mole ratio between the two? N2 is 1, this one's 2. That means that for every 1 mole of N2, we need 2 moles of NH3. And if we used up 1.5 moles of N2, that means we had to use twice up. We had to have a change of twice as much of NH3. And so that means we know we had a change of 3.0 molar was the concentration change for the ammonia. And for the H2, for the hydrogen, it would be 3 times as much because it has a mole ratio of 1 to 3 right here. And so that's a 3. And so that means we'd have 4.5 molar would be the concentration change of the hydrogen here. And so that's how you go about figuring out concentration changes. It's a little difficult, once again, to explain this by talking about it. Let's work out an example, and that'll give a little better indication on how that works. So let's take a look. So just as a note, the technique that we're using to determine this is called the mass action expression. The mass action deals with our calculation for KEQ, and we'll use a particular technique here that'll help us out. So we are told here 3 moles each of gaseous carbonic acid are placed in a 6-liter container. If the decomposition reaction is reversible and 1.2 moles of CO2 are found after the reaction reaches equilibrium, what are the equilibrium concentrations? So here's basically the way this works. The first step is, if it's not written out for you, write out the chemical equation, same as it has been on stuff before. And so it's decomposition of carbonic acid. Carbonic acid, this is the one we've dealt with a lot on these things right here. So H2CO3 is what that is. It's a reversible reaction. So we have the double-headed arrow on this. And carbonic acid decomposes into carbon dioxide and water vapor. Let's look at what we have for our coefficients. We have 2 hydrogens on one side, 2 on the other, 1 carbon on the left, 1 carbon on the right, 3 oxygens on the left, and 3 on the right, so we're already balanced. And so the first thing you want to do whenever you're setting up one of these mass action expressions here is you're going to write down 3 sections here. The first section you're going to be dealing with is basically going to be your before section. And so we'll call it a B for before here. Then you're going to have your change, and then you're going to have your basically your final down here. And what we know is if you take the before and add the change, that'll give you the final. All right? So let's write down what we know. Is we have 3 moles each of gaseous carbon dioxide. And so really it shouldn't be each, it should be 3 moles. So get rid of that each right there. We don't like that anymore. So 3 moles of gaseous carbon dioxide, gaseous carbonic acid are placed in a 6-liter container. What you want to write down for each of these is you're going to write down the concentrations, because we're really not interested in how many moles. We're interested in what the molarity is, the concentration here. And so if we have 3 moles in a 6-liter container, that's going to give us a molarity of 0.5. So we started off with a carbonic acid with a molarity of 0.5 here. And that's what we start with. Now it says that this is what's placed in here. So how much carbon dioxide we have originally? Didn't say we placed any, so we don't have any carbon dioxide to start with. What about water vapor? Did we place any water vapor to start with? Nope. And so to start off with, and this is normally how we start reactions, we don't put everything in there, we just put things on one side. So we put carbonic acid in here. And since this is a reversible reaction, this reaction will start off by flowing to the right side, and so that the concentration of carbonic acid decreases, the concentration of the carbon dioxide in the water is going to increase. But how much? Well, we know that there are 1.2 moles of carbon dioxide are found after the reaction reaches equilibrium. So if we were to look at sort of our final amounts here, we know that afterwards there are 1.2 moles of carbon dioxide, but we don't want moles, we want molarity, concentration. So we take our 1.2 moles and divide it by the size of our container, which is 6 liters. And so that's 0.2 if you do that math here. And so we know we end up with 0.2 molarity concentration of our carbon dioxide. And this is all we know right now. So we say, what are we going to do here? Well, we could find one of the changes, because for the carbon dioxide, we know the original amount, which is the 0. We know the final concentration, which is 0.2. And so we know the change in this one had to be plus 0.2. We know that's the case. But now that we know the change, here's where the magic comes in. Because of the fact that the change of the carbon dioxide is 0.2, we know that change is going to be in mole ratio with all the other ones. And so the coefficient of the carbon dioxide is 1. It's not really there. And the coefficient of the water is 1. And so there's a 1-to-1 mole ratio between those two. And so that means that if the carbon dioxide gained 0.2, it means the water has to also gain 0.2, right? And the mole ratio of the carbon dioxide to the carbonic acid is also a 1-to-1 ratio, because they both have coefficients of 1, which means that the mole ratio between those two also has to be 0.2. But since the reaction goes from left to right, the carbon dioxide and the water vapor were gaining, the carbonic acid was losing. And so instead of gaining 0.2, it's going to lose 0.2. And if this one right here loses 0.2, then this lets us now go ahead and figure out what the final concentrations, the equilibrium concentrations are all of them. And I called it a final. It really should be an equilibrium concentration down here. That's what I probably ought to call that. So with the carbonic acid, it started off at 0.5 and it's lost 0.2. So now its concentration is 0.3 molar. So I've got that. The carbon dioxide, I already knew what its concentration was. It was 0.2 molar. The water vapor, or the water, it is water vapor because all these are gases in this case. 0 plus 0.2, I get 0.2 molar are my concentrations. So the question is, what are the equilibrium concentrations? These are them right there. I have 0.3 molar carbonic acid, 0.2 molar carbon dioxide, and 0.2 molar water. And so those are the concentrations I have of each one of these at equilibrium. If I wanted to find KEQ, I can now do that because I now know what all my equilibrium concentrations are. That's basically how you're going to set up one of these moving to equilibrium type problems. So let's work out another example like this. So here's what we know. In the reversible reaction below, 2 moles each of A and B are added to a 1-liter container to start the reaction. At equilibrium, 0.6 moles of C are measured. What is the equilibrium constant? In this case right here, we do not know what the substances are, and the fact we have 3A plus B yields reversibly 2C plus D. They are all gases. Typically, in order for these types of reactions to work, we're talking about molarities, but we're talking about more gas molarities. So in all these cases we've been doing here, these all are generally gases. So let's set this up, that we know that we want to start off with our before, we're interested in our change, and we want to get to equilibrium. And so that's what we're dealing with here. So let's take a look. Do we know the amount of A we had before? It tells us we added 2 moles each of A and B, and we had a 1 liter container. We want the molarity. We want to have the concentrations. And so molarity is moles, and for A, it'll be moles of A divided by the liters. 2 divided by 1 is just 2. That makes this easy. So we have a 2 right there. B is the same thing. We have 2 moles of it divided by 1 liter. It gives us 2 for the concentration of that. It says that we're adding just these 2 to start it, and so for C and D, we don't have any concentration. There's 0 of both those 2. The molarity is 0 for these guys. Looking for our final amounts, equilibrium amounts, it tells us that at equilibrium 0.6 moles of C are measured. And so we say 0.6 divided by the 1 liter gives us 0.6. So I get 0.6 for C in this case, and this is what I have to start with. It's all the information I have. I want to find the equilibrium constant. To find the equilibrium constant, we have to know the equilibrium concentrations. And right now, we only know C. So our next step will be saying, all right, what is the change in C? C started off at 0, ended up at 0.6, and since it started at 0 and ended at 0.6, that means the change must be 0.6. And so that's going to be our change in C, and it's going to be plus 0.6. It's positive here, which makes sense because we expect that when this reaction started off, entirely weighted to the left side with A and B having stuff but C and D not having anything, and so this reaction is going to flow right. So we're going to see positive changes for C and D. We're going to see negative changes for A and B because it's flowing away from A and B. So let's look at what we got set up here. Let's look at D because we know it's going to be our other positive one, so we know it's going to be positive right here. But we got to figure out what the change is going to be. Well, let's look at the mole ratio between C and D. C has 2, D has 1. So that means that the mole ratio from C to D is going to be a 2 to 1 mole ratio. And so we will have half as much D as we do C. And so in this case, instead of being 0.6, it'll be half of that, 0.3, because that would be a 1 to 2 mole ratio from D to C. And so that works out there. For A and B, let's take a look at B first, because it looks a little simpler here. The mole ratio from C to B is also a 2 to 1 mole ratio, and so it's going to be 0.3 as well. Only in this case, it's going to be negative 0.3 because, once again, it's flowing away from that A to B side. That's where it started. It's going to flow away from it because, well, it can't flow from right to left because it had there's 0 concentration to start with on the right side. So we've got that. Now for A in this case right here is their 3A to 2C, so that's a 3 to 2 A to C ratio. And so if you work out that ratio here, as we know that that a 1 would be 0.3, and so based on what we found before here, and so we have 3 times that for A, so that'll be 0.9. And so it's going to subtract off 0.9 here. And once we've got that, now we can go ahead and figure the equilibrium concentrations. 2 minus 0.9 is 1.1. 2 minus 0.3 is 1.7. We've already got the carbon, the C, and then D, 0 plus 0.3 is 0.3. Now we have all the molarities of each of the concentrations at equilibrium. All the concentrations in molarity at equilibrium. The question is, what's the equilibrium constant? And so to find KEQ, remember that we want to take the concentrations of the right side first, and so that's going to be 0.6 for our first one for the C, and since its coefficient is 2, it's going to be 0.6 squared, times the concentration of D, which is 0.3, which has no coefficient's 1, so it's just 0.3, divided by, let's look over on the left side, because the left side's always on bottom when you're solving for KEQ, and we have a concentration of 1.1, and that one is, since the coefficient's 3, it'll be 1.1 to the third power, times the concentration of B, which is 1.7 at equilibrium. And that one is, since the coefficient of B is a 1, it's just 1.7. And now it's just basically go ahead and do the math on it. And so when we're setting this up, we say 0.6 squared times 0.3, then divided by, on the bottom, 1.1 cubed, and then divided by 1.7. And when we do that, I get a KEQ of 0.0477. 0.0477. For significant figures, we have 2 moles up here, and so that's only 1 sig fig, and so that went into our calculations here. And so our final answer here would be 0.05 would be our final value of KEQ that we get right here. And that's how you'd go ahead and use that mass action expression to go ahead and find an equilibrium constant. So let's go on a little farther here. What if you're missing more information than what we've locked here? Is that what if we know the equilibrium constant and we know the initial concentrations, but we don't know anything about the final concentrations? We lack all that information. If we don't know the final concentrations, then it really sort of puts us a little bit in a little bit of a difficult position, because without the final concentrations, without those equilibrium concentrations, we can't find the change. And without the change, then we can't find the other changes. And so then we can't find any equilibrium concentrations. And so using our previous method, we're sort of stuck. But there is a little mathematical trick that we can use, using some approximations that work under the case that if KEQ is very large, over 100 or so, roughly, it needs to be large, and the reaction starts on the right side of the reaction. So if KEQ is large and the reaction starts on the right, we can use this trick. Or if KEQ is small, like less than 10 to the negative third, and the reaction starts on the left. So if KEQ is big and the reaction starts on the right, we can use this trick. Or if KEQ is small and starts on the left, we can use this trick. So in this method, the changes in concentration are written in terms of an unknown, x, because we do not know what the final concentration is, the equilibrium concentration, so we can't find numbers for any of the changes, but we can write them in terms of our unknown x. And this variable will be substituted into the equilibrium constant equation. So we're going to basically find what the equilibrium concentrations are in terms of x, then put it into KEQ, and then solve for x for there. So solving for x lets us determine the equilibrium concentrations then. And so let's show how this has worked. This does get a little bit complex on this, but if you just follow it through, it works out just fine. So we've got this case right here. 5 moles each of A and B were inserted into a 20-liter container to start a reversible reaction. If KEQ equals 4.2 times 10 to the negative fourth, what are the equilibrium concentrations of each substance? So our reaction is 2A plus 3B is reversible to C. And so we want to set this up the same way we did the other ones before. And so we have a before, we have a change, and we have an equilibrium amount. All right? And so we're told that we have 5 moles each of A and B to start off with here in a 20-liter container. We need to find the initial concentrations. And so for the initial concentrations here, we say we have 5 moles divided by 20, and we do that, we get 0.25. So my before concentration of A is 0.25, my before concentration of B is 0.25, my before concentration of C is going to be 0 because I didn't have any C to start with here. All right. So, do we know anything about the equilibrium concentration? Not a 1. We don't have any information about that. And so what we're going to do is we're going to call the change basically x for one of these substances. And in this case right here, A has a coefficient of 2, B has a coefficient of 3, C has a coefficient of 1. Since C has a coefficient of 1, we're going to call the change in C x. Okay? Now, since the fact that this reaction starts on the left because we have 0.25 of both of them to start with, is that we can set this up this way. It's going to go from left to right. That means this is going to be positive x. Okay? That means that the change in B, we start off at 0.25 for the concentration, is going to have to be in mole ratio with that x change that we had for C. And so C has a coefficient of 1, B has a coefficient of 3, and so that's going to be a 1 to 3 ratio. And so if C gained x, B is going to lose 3x, like that. And A, since it's got a 2 to 1 ratio from A to C, if C gained x, A has to lose 2x. That should sort of make sense for right now, is that we don't know what it is, but we know they have to be in that ratio of a 2 to 3 to 1 ratio because the coefficients are 2 to 3 to 1 ratio. So, do we know what the equilibrium constants are? Not the numbers for them, we do know them in terms of x. C is going to be just x, so 0 plus x is x. B, though, is going to be 0.25 minus 3x. For it, the equilibrium concentration for A is going to be 0.25 minus 2x. Ooh, we don't like that, but that's what we've got for right now. Question is, what are the equilibrium concentrations for each substance? And so we know the equilibrium concentrations here. We know that KEQ is 4.2 times 10 to the negative fourth. Now, let's set this up by solving for KEQ in terms of x. And so we know KEQ is 4.2 times 10 to the negative fourth. So 4.2 times 10 to the negative fourth. And this is going to equal to the ones on the right. There's only one that's on the right here. That's our x. And so we have x on top, our concentration x that's right there. It's raised to the power of the coefficient. In this case, that's just 1. Divided by the guys on bottom. And so the first one that's on bottom will be the first one that's on the left. And so that's going to be 0.25 minus 2x raised to what power? Raised to the second power. I'll continue that over there. Then also divided by our B concentration equilibrium, which is 0.25 minus 3x to the coefficient there, which is 3 to the third. Oh boy. Could we solve this? Actually, we probably couldn't, just by doing the math straight up here. Because the problem we run into is, I mean, if you look at this, if we multiply those two terms on the bottom, we're going to get something that has an x to the fifth power. And so we're going to end up with basically a quintic equation here, and you don't have a way of solving quintic equations for x. You could do a quadratic equation, and there are methods for even solving cubic equations, but anything above x to the fourth power, there's no general way to find the solution. And so it sort of seems like we are stuck a little bit here, except for one thing. Remember that we said that in order for get this technique to work is that if your equation started on the left, that you needed a KEQ that was very small. In this case right here, our KEQ is 4.2 times 10 to the negative fourth. This is a very, very small value of KEQ. And if you also remember our definition of KEQ, we said that when KEQ is small, it means the reaction favors the left side very heavily. And if this reaction favors the left side very heavily, since it starts off on the left side, it means there won't be a whole lot of change. That means x is very, very small. Whatever this change is, it's got to be tiny. And if x is very, very small, then we can do a little bit of an approximation. Because let's look at this term that's on the bottom here. We have 0.25 minus 2x. If x is tiny, like 0.00001 or something like that, then 0.25 minus a really tiny number is basically the same as just having 0.25. And so the same thing is true over here. If x is a very, very tiny number, then 0.25 minus 3x, if x is really tiny, is basically the same as 0.25. We can basically do an approximation here. And if we do this approximation, then we can rewrite this a little bit. So we say 4.2 times 10 to the negative fourth is going to be equal to x over, but in this case we've done our approximation. Our approximation is 0.25 times 0.25. This one we can definitely solve. And so note that we can't go ahead and assume that top x is going to disappear because it's by itself. This is only something that works comparatively, is that that 0.25 minus 0.0001 is basically 0.25, but that's not the same as saying 0.0001 divided by something is the same as 0 divided by something. Those aren't true at all. This only works whenever we've got something minus something else or something plus something else. But we can go ahead and solve the one we've got up here at top, and so we'd say 0.25, oops, I forgot something here. It's 0.25 squared here and 0.25 cubed here, because remember these coefficients are still there. And so we'd say 0.25 squared times 0.25 cubed in this case, or you could have just done 0.25 to the fifth in both cases. Then we're going to multiply that up. So times 4.2 times 10 to the negative fourth. And so if we do that, we get something that's a really, really tiny number. And so in this case, let's see if I can count my decimals over. 1, 2, 3, 4, 5, 6, 7. So I get that x is equal to 4.1 times 10 to the negative seventh. And if that's true, then is it reasonable that I would have ended up, that my assumption here is 0.25 minus 2 times 4.1 times 10 to the negative seventh, basically 0.25? Most definitely. It's basically going to be 0.249999. I mean, it's going to be some incredibly number. It's very, very close to 0.25. This is a reasonable approximation to make. And if this is the case, the question is, what's the equilibrium concentrations of each substance? And so here is that we started off here with the equilibrium concentration of A was 0.25 minus 2x. Well, 0.25 minus 2x is basically going to be, since x is so small, 4.1 times the negative seventh is basically 0.25 molar. For our second one, 0.25 minus 3x, it's going to be the same thing. It's going to be 0.25 molar in this case because that's basically the same thing. But for our last one is just x. X we just found is 4.1 times 10 to the negative 7th molar. And so because of the fact that KEQ was so small that we could basically work out all our answers here, and I guess technically we probably ought to, since this was 20-liter container, we should have rounded this to 1 sigma-unit figure, so it probably should be 0.3 molar, 0.3 molar, and 4 times 10 to the negative 7th. But you get the basic idea on how this sets up. What you want to do in this case is set up the equation the same way we had before, only with our variable x in the place of the change, set to the mole ratios. And then once you've written out your KEQ equation, you want to look for cases where that your value of KEQ is going to let you do an approximation. It's going to, if your x is either going to be very, very small in some cases, well, it basically will be very, very small. And with that very, very small x, things that are differences like 0.25 minus 2x or 0.25 minus 3x, you can basically approximate to be just like the 0.25 here. So let's try out another one of these to make sure we get a little bit of practice on this. And it works very, very similar to this last one and get a little more practice on it. All right. In a reaction with an equilibrium constant of 2089, 0.3 moles of CO2 is added to a 10-liter container to start the reversible reaction below. What are the final concentrations of carbon monoxide and oxygen gas? So we have 2CO plus O2 reversibly yields 2CO2. And so we're going to set this up the same way that we had before, in that we want to have our before, we want to have our change, and we want to have our equilibrium position here. And so what do we know to start with? We have 0.3 moles of CO2 that are added to start the reversible reaction here. So we have 0.3 moles. As the number of moles, the container is 10 liters, though apparently I can't tell the difference between a 0 and an O on my keyboard. So that gives us 0.03 for the concentration of CO2 to start with. So we have 0.03 molar carbon dioxide to start with here. It says we're starting by adding this. That means we have no oxygen to start with, no carbon monoxide to start with. And we likewise have no idea what we have for our equilibrium concentrations. And that means we don't know what our changes are either. We do know that since we started off with 0.03 molar stuff over here, is that this one is going to go, since it starts off with 0.03 molar on the right, this one is going to have to basically start off by going left. And so that means that the carbon dioxide is going to lose, and the carbon monoxide, the CO, and the oxygen are going to gain in their change. Of the three things, we have two carbon monoxides, one oxygen, 2 carbon dioxide. So our change here we'll probably do the oxygen first because it's got a 1 for its coefficient. And so its change is going to be x. We're going to add x on this one. And since the mole ratio from oxygen is 1, for carbon dioxide is 2, so it's a 1-to-2 ratio here. This will be 2x for this guy right here. And then for our last one, our 0.03, is that we know it's going to end up being, since that's got a 2 for the coefficient, it's a 1-to-2 ratio, it'll be minus 2x. So for our final concentrations, we have 2x for carbon monoxide, x for oxygen, and 0.03 minus 2x for the carbon dioxide. So let's go ahead and let's set up our equilibrium equation. Our equilibrium constant equation. So we have 2089 is our equilibrium concentration, is equal to the things on the right. On the right now we have 0.03 minus 2x raised to the coefficient, which is 2, second power, divided by the things on the bottom, which are carbon monoxide, which has a concentration at equilibrium of 2x, but since its coefficient is 2, it'll be 2x squared. And then the oxygen has a concentration of x. Since it's just a coefficient of 1 out front, it's just x by itself. Once again, we probably really don't want to have to solve this. Let's see if we can use one of our tricks here. Well, we know that the equilibrium constant is 2089. It's not small like the last one, but unlike the last one, this guy right over here starts on the right side. And we know that the rule is that if your reaction starts on the right side and your equilibrium constant is large, we can use our trick here. Because if the equilibrium constant is large, that means the reaction wants to stay on the right side. And if it wants to stay on the right side, that means x is once again going to be very, very small. And if x is very, very small, then it means that our little trick right here, 0.03 minus 2x, if x is very small, then it means that that is basically the same as just having 0.03. And so this is going to be our little trick here, because if x is small, and it has to be if it's going to have a very large KEQ, then basically this is equal to 0.03. And so we can rewrite this guy as 2089 is equal to just 0.03 squared divided by, on bottom we have 2x squared, which is 2x quantity squared, which is just 4x squared times x. So that would be 4x cubed on bottom. And so at this point, we can just sort of solve for x. Let's multiply x up. And so we have 2089 times 4x cubed. And so that ends up being 8356. X cubed is equal to 0.03 squared. And so divide both sides by 8356. 8356. And so when we do that, we say 0.03 squared divided by 8356, and I get that x cubed is equal to, let's see, much I got to count here, 1, 2, 3, 4, 5, 6, 7, 1.08 times 10 to the negative 7th, and then I got to take the cube root of that, so raised to the 1/3 power, or just take the cube root if your calculator does that. And so in this case right here, I get x is equal to 0.00475. We have 0.3 moles to start off with this one here. 10 liters, all one significant figure. So our answer right here would be rounded to 0.005 would be my x value here, is what I get for that. Now for my x, but the question asks for what the final concentrations are. And so if this is the final concentration here, we got to find them for all ones. So for the carbon dioxide right up here, it's 2x is what that is. We got that right here. And so for the concentration of the carbon monoxide is basically going to be equal to 2 times this guy right here. So times 2. And so for that concentration, they just basically get 0.0. Actually be 0.0095, which since it's one significant figure would be 0.01. Okay, molar. For the oxygen's concentration would be just x, so that would be 0.005. Okay, molar. For our last one here, the CO2, well, we said x is very, very small here, and so it would be basically 0.03 minus 0.005 times 2. 0.005 times 2 is 0.1. And so for our last concentration, for our carbon dioxide concentration, CO2, if I can get that to fit in here, is basically going to equal to 0.02 is what we get here. This one's probably pretty borderline about being able to use this technique, because you see that x was decent size compared to the 0.03 at the very end. It did reduce it by about 1/3 here, but and it does tend to, the closer that you get to a reasonable size, the farther off this deviates from being perfect. But this technique works pretty well if you have a case where you're trying to solve for an unknown and you really don't have enough information to use it. If these two things that are true, that you have an equilibrium constant that's either very small and it starts off on the left, or it's very large and it starts off on the right. But this is basically the technique that you use. One of these two guys, either using the technique we started at the beginning of this lesson or this one right here, will both get you through to what you're looking for here. And so that's what we've got for that one. And that right there, I believe, finishes up this lesson.